Welcome back to the deep dive. We're jumping back into the online encyclopedia of integer sequences today. You know, that amazing resource for number patterns, and this one's especially for you number theory students out there. We're looking at sequence A000285. So what is A000285? Okay, it starts AL is 1, A1 is 4. Pretty simple. Then for n greater than or equal to 2, you just get the next term by adding the previous two, an1 plus an2. So the first few terms go 1, 4, 5, 9, 14, 23, 37, 60, and so on. Okay, let's unpack this. That recurrence relation, an1 plus an2, that looks really familiar, doesn't it?
It absolutely does. It's the Fibonacci recurrence relation. But what's fascinating here really is those starting values, 1 and 4. They make it completely distinct from the standard Fibonacci sequence. It's brought this on back in '78, actually called sequences like this Pseudo-Fibonacci numbers.
Pseudo-Fibonacci, okay.
Exactly, because they use the same rule. But those different starting seeds, 1 and 4, I mean, you get a totally unique sequence. It really stands on its own.
Right, so it branches off. Interesting. So digging into it, how does it connect to other big names in sequences? Like, is it related to the actual Fibonacci numbers or maybe Lucas numbers?
Oh, definitely. It's deeply connected. You can actually express A000285 directly using both. For instance, one neat formula is AN equals Fibonaccian plus Lucas n plus 1.
Ah, okay, so a direct link.
Yes. Or another way to put it is AN equals 2 times Fibonaccian plus Fibonaccian plus 2. It really shows how these sequences, they're all part of this bigger mathematical family. They reflect each other in interesting ways.
That makes sense. So beyond just how it relates to others, what about the sequence itself? Does A000285 have any, unique properties that make it stand out? Anything surprising?
Oh, absolutely. This is where it gets quite intriguing. Did you know that in the entire sequence, starting from A0, the only perfect squares are the terms 1, 4, and 9?
Wow, just those three, A1 and A3.
Just those three in the positive sequence. If you look at the negative indices, which you can do with this recurrence, A9 is 81. That's the only other one.
Okay, so very few squares.
Very few. And perhaps even more striking, it's been proven that no term in this sequence, positive or negative index, is ever twice a square.
Never twice a square. That seems oddly specific.
It is specific. And proving things like that often involves some pretty deep number theory. It tells you something fundamental about the arithmetic nature of A00000285, setting it apart.
That's really quite something. Okay, so we have these theoretical properties, these connections, but does the sequence A000285 ever show up somewhere more tangible, like in combinatorics or geometry? Can we sort of visualize it?
We can, actually. There's a wonderful combinatorial interpretation. For n greater than 2, it turns out that an plus or minus 1, depending on n specifically, plus make it 1 raised to the power of ceiling n2.
Okay.
That number counts the ways you can tile a strip of lengths n1, but not just any strip one with a sort of central staircase pattern, and you're tiling it using just simple unit squares and dominoes.
Tiling a staircase strip, that's unexpected.
Isn't it? It connects this abstract sequence to a very concrete visual problem. It also pops up as sums along certain diagonals, the SWNE ones, and what's called the 4-1 Pascal triangle. That's another sequence, A093561.
So it has connections to tiling and a variant of Pascal's triangle. Fascinating. It really is amazing how just changing those first two numbers, 1 and 4, takes that familiar Fibonacci rule and creates something with its own unique character, its own mathematical fingerprint, and even these surprising applications. So as you continue exploring number theory, what's the takeaway here?
I think the main takeaway is just how sensitive these recurrence relations can be to their initial conditions. A tiny tweak at the start, like using 1 and 4 instead of 0 and 1, unlocks this whole different world of properties and connections. It's a great reminder, really. Keep digging in the OEIS. Keep looking for those variations. You never know what hidden patterns or surprising links you might uncover just by changing one small thing. Keep exploring.